Okay, so in this video, we're going to look at section 3.3, the case where the characteristic equation leads to complex roots. Okay, and so we wrote down the general solution that we get for the case of complex roots. And now let's solve this problem, this initial value problem. So in the book, you'll see example 1 and 2 in the book that are in contrast in the sense that in example 1 in the book, the real part is negative, okay? And example 2, the real part is positive. And based on the real part of the root being positive or negative dictates the behavior of the solution, okay? And so in example 1 from the book, the real part was negative, and so solutions would decay to 0, but oscillate, okay? Similar to the example that we looked at in lecture. In this example, we'll see something different. So to solve this, our characteristic equation is r squared minus 4r plus 5 equals 0, okay? And I can do the same trick that I did in lecture where I can write this as r squared minus 4r plus 4 plus 1 equals 0. And you'll note that this is a perfect square. This is r minus 2 quantity squared. Okay, and I can move that plus 1 over to the right-hand side and write it as minus 1. All right, take a square root of both sides, all right, so that we have r minus 2 equals I plus or minus I. And then I can add 2 to both sides. So this leads to roots being 2 plus or minus I. Okay? And you can check that this is true with a quadratic formula. So this leads to a general solution of the form, so y of t equals c1 e to the 2t cosine of t, okay? And then plus c2 e to the 2t sine of t, right? So this is the general solution, and now we have initial conditions so that we can solve for c1 and c2, all right? So to do that, we need to find y prime. And so y prime, and of course it's tedious to compute y prime. Nonetheless, we have c1 times, we need to use the product rule, so the product rule is derivative of the first, which is 2 e to the 2t times the second cosine t, and then plus the first times the derivative of the second, which is going to be minus. We get a minus from the derivative of the cosine being minus sine. Okay, so this is the derivative of the first term, and then plus c2 times the derivative of the second term is, let's see, 2 e to the 2t sine of t, and now plus e to the 2t cosine t. Okay. All right. So this is the derivative. So we have y and y prime. And now using the initial conditions, we can get two linear equations for the two unknowns c1 and c2. So y of 0, if I plug 0 into this general solution, the sine term is 0. That's nice. The cosine term is not 0, but it's nice in that e to the 0 is 1, cosine of 0 is 1. We just get c1. And so now c1, well, must equal 1. Okay? We use a second initial condition, y prime of 0. Okay. So now if we evaluate the derivative at 0, the c1 term turns out to be a 2c1. Okay? The sign here is, this drops out. This is all 1 times 2. So we get a 2c1 from there. And then the c2 term is, okay, so now this is the sign term that cancels, and this here turns out to be a positive 1. So it looks like we get plus c2, okay? And this must equal 5. So knowing that c1 is 1, we can plug that in, and it looks like c2 must be 3. So our solution is y of t equals e to the 2t cosine of t, and then plus 3 e to the 2t sine of t. So this is our solution, and as I said, the real part of our of the roots is positive. So now we don't get oscillations that decay to 0, we get oscillations that will blow up. Okay, so notice the difference in the behavior based on what the roots are, or the real part of the roots.